Hello, this is Brian Washburn. I like to talk about Lagrangian multipliers. Okay, so one thing, one advantage of Lagrangian mechanics is that we don't have to consider forces in general. All we have to do is consider kinetic energy, potential energy, and equations of constraint. However, sometimes it's important to get forces out of it because forces are very physical, and we may need to understand something a bit about forces in a specific problem. Now, so either that's a disadvantage or a disadvantage of Lagrangian mechanics. It's an advantage because when you don't have to consider forces. However, if you really need forces, or more specifically, if you really need the forces of constraint, then Lagrangian mechanics has a severe disadvantage to that. You can get the forces of constraint, but it's actually a little complicated to do so. So what I'd like to do is talk about how you can get forces out of Lagrangian mechanics, and then specifically talk about how you're going to get forces of constraint from Lagrangian mechanics. Now, previously we defined a generalized force. If I have a variable q, I can define the generalized force p f sub q as equal to partial L respect to q. Okay, that's my generalized force, and that may be a force or a torque, or it might be something else. So it depends. So really, generalized forces are hard to interpret because you might get something that might look like a force, or it might be other stuff that's not physically a force. Is this thing here, if I take this, I can always take the derivative. Is this the result of that derivative? Is it really physically a force or torque? And that's what's really hard to determine. And we saw examples in class where sometimes that derivative is the force. For example, for simple harmonic motion, that will be the spring force acting on it. Some of our problems, it's a combination of a real force plus some other stuff. Now, usually what happens is with that force, when I take this derivative, I'll get the force associated with a potential. Okay, and you may say, well, why is that? Well, because let's remember the potential energy is just a function of, say I have this situation here that the potential energy is just a function of position, the kinetic energy is just a function of velocity. Okay, so then if I take the partial of u respect to x, I said L respect to x, that's going to be equal partial to u respect to x, okay? And that's going to give me minus the conservative force that creates that. So that's for a conservative system. But so then that generalized force is the force acting on, well, actually it's the conservative force, okay? However, it doesn't give us any information about equations of constraint or forces of constraint. So what we're going to see here is that we're going to learn a method called the Lagrangian multiplier method that relates for every equation of constraint. Okay, so there's going to be a relationship between equations of constraint and a force. Okay, so if I have one equation of constraint, there's a force or maybe even forces that create that equation of constraint. So we can use that information to actually get the forces that cause that equation of constraint to show up. Okay, so that's what we're going to talk about next. So we're going to use a method called the method of Lagrangian multipliers. This is a more general method that falls in the branch of the calculus of variations, and we're going to use these to get the constraint forces. Okay, so what we're going to show in class is that if I have, so delta is what's called a Lagrangian multiplier, and I can modify the Euler-Lagrange equations to put these multipliers in. And once I have the multipliers in, then I can calc an equation of constraint. So f sub x is the x component of the force of constraint is going to be equal to the multiplier I get from solving the Euler-Lagrange equation plus the partial derivative of f respect to x. Now, what is f? Just to remind you, f is an equation of constraint. So in the end, I'm going to have f is going to be a function of my Cartesian coordinates x, y, z, and I always can write that in the form of some function of x, y, z equal to 0. Okay, I want to show you an example in a minute. Now then the question is, how do you get the Lagrangian multipliers? Because once I know f, I can take derivatives of f. how to get the Lagrangian multipliers, I need to solve a modified form of the Euler-Lagrange equation, which I have listed here. Okay, and we'll derive in class how do we get this modified equation here. All right. Now, life is not so simple, especially if we have more than one generalized coordinates. So, say I have, say q sub j is my generalized coordinate, and I have s of these. Remember, if I have one generalized coordinate for each degree of freedom, I'm going to get s Euler-Lagrange equations for each q sub j. And so then I'm going to generalize the equation I had, the Euler-Lagrange equation before. So I have this is the same Euler-Lagrange equation I had before, except I have this new term here. Okay, and so you can see here, this is my new term here. Notice that the sum is over k. Remember, what I have is my equations of constraint are really, I have k is the index of these, so I have m equations of constraint. M goes from, and then k goes from 1 to m. And then this guy here is going to be a function of all my Cartesian coordinates. In this case, I'm going to write x sub I, where I is 1, 2, 3 for x, y, z. Okay. And so then, for each equation of constraint, I'm going to have a multiplier associated with each equation constraint, so it's delta sub k. And I have to take the derivative, partial derivative of f with respect to the generalized coordinate q. Now, you may say that, well, in general, when I write my equations of constraint, they're in terms of x's, the Cartesian coordinates, but also I remember I have a bunch of equations that relate my Cartesian coordinates xi to all my q's. Well, they might be a function of q's, so that's q sub j. Also, they may be a function of q dot dot, and it may be functions of time as well. So this can get pretty messy. All right. So then once I have all my k or m lambda sub k's, I can calculate my generalized force. So the generalized force associated with that is just going to be sum over those, each one of those times the partial derivative of f with respect to k q sub j. So this looks messy. Actually, it's and for multiple dimensions it can be really messy. Okay. But it does allow us to solve for the Lagrangian multipliers. Once I know the Lagrangian multipliers, I can get the forces. Now, I'm going over this method as just for completeness. Your book talks about this. In general, this is very complicated to do. The other problem is that you're going to get these multipliers. That's not the hard part. You can take the derivatives, but then interpreting the results is very difficult. And in the end, it's just best to use Newton's equations to interpret the results. Okay, so the point I'm trying to make is that you can get the forces of constraint using Lagrangian methods. However, physically interpreting what those things are is very difficult without solving Newton's equations to begin with. So you might as well just solve Newton's equations to get those forces. Usually, what people do is they get the equations of motion using Lagrangian methods that we've done before. You get the equations of motion, and then you can use those to help you guide your solution using Newton's equations to get the forces of constraint using F equals ma. That's one method of solving these types of problems. So let me just solve a problem for a simple pendulum, okay, using Lagrangian multipliers. Okay, so this is a simple pendulum. And remember, so I have a free body diagram just written up on the top. Let's kind of look over that a little bit. Remember what forces act on it. I have gravity acting downward, and I have a tension that's along the length of the string. So my constraining force is the tension T. Okay. Now that constraining force leads to an equation of constraint, and that equation of constraint is just the fact that the mass moves along a circle of radius L, the length of the string. So sorry about that. This is my equation of constraint right here, okay? And that says basically that's the equation of a circle that the pendulum mass follows. All right, so that's my F. There's only one equation constraint. Now, since my equation constraints in terms of Cartesian coordinates, I'm going to write down my Lagrangian also in the form of Cartesian coordinates, and that's just going to be the kinetic energy in x direction, y direction, and then potential energy. And you notice I have the x pointing down and y pointing to the right. So now even though this is a one-dimensional problem, to get the multipliers, I have to actually make the problem harder and write it as a two-dimensional Lagrangian. Thus, I'm going to get two Euler-Lagrange equations. However, since I have one equation constraint, this guy here, I'm only going to have one delta. Okay, so my first modified Euler-Lagrange equation looks like this. That's easy to figure out. Partial L with respect to x, that's mg. The derivative of partial L with respect to x dot, that's just mx double dot. And then delta times partial f with respect to x, that's going to give me, from this term here, only 2x. So I get this equation here. All right, so this is my equation of motion. Now, we're not going to solve it, but what we're going to do is we're going to compare this to F equals ma. So F equals ma, again, I have tension and mg. Okay, so notice that in the x direction, I have mass times acceleration in the x direction is going to be equal to, well, mg, that's downward. And then t, I'm going to call this a tension, and the component of tension in the x direction is t cosine theta. Now, remember that I have relationships between x is going to be equal to L cosine phi, and y is going to be equal to L sine phi. So then what I can do is I can solve for cosine phi is just going to be equal to x over L. If I stick that in place of that, I get this expression here. Now take a look at this equation here and this equation here. Notice at the end I can relate basically now this term here with this term, and that allows me to solve for the multiplier, and the multiplier is going to be minus capital T divided by 2L, and that's what I have highlighted here. Okay, so that's that. Now let's look at the second equation. So we solved for the multiplier. Unfortunately, we had to use Newton's laws to do that. That's okay. I'm going to look at this equation here. Notice I have the same multiplier. I should get the same result. I get, for that equation of motion, is my double dot times delta, or lambda 2y. Okay. Now, using F equals ma, I got the only force acting in the y direction is minus t sine. Using this relationship here, I can say that, well, sine of phi is this going to be y over L. Okay. Okay, and then so, oops, sorry about that. So I compare now. Then what I do, I look at this term here to this term there, and I get the same result, that lambda is equal to minus t 2 over L. So I've solved the multiplier. I can now get the equations of constraint by taking those derivatives. So now let's say the F component, so the constraining force, the X component of the constraining force is going to be equal to the F component constraining force is going to be the multiplier times this partial derivative. I stick everything in. Now again, instead of having x, I'm going to use L cosine theta. The L's cancel out, the 2's cancel out, and I get minus t cosine phi, sorry. And that's just the x component of the tension. I do the same thing for y. Again, I have the same multiplier, partial f respect to y, that's 2y. And then I get minus t sine phi, that's the y component of the tension. So that's how you use these multipliers. That was a complicated, annoying problem even for one dimension. I'm not going to even think about doing a more complicated problem because it gets just too hairy. But in the end, you can see how you can use this to get the forces of constraint. Okay, so don't forget Newton's laws. All right, that's the moral of the story. All right, take care. We'll see you later. Bye-bye.